Welcome to tutorial 4.3, parts 3 and 4. The reason 3 and 4 are combined is both of these sections on the website where you practice are about writing ionic equations, but for part 3 you write the complete ionic equation, and in part 4 you write the net ionic equation. So first let's just review again what ionic equations are. As in the case with precipitation reaction, we started off with writing just molecular equations. We did the same for the acid-base reactions. We just wrote molecular equations in 4.3 part 2. However, again, like precipitation reactions, it's also kind of nice to keep track of what the ions are that are actually in the solution, and also to write net ionic equations to show what actually is happening, which positive and which negative ions are actually coming together and what's happening to them. What makes it a little tricky here with acid base is because you have strong electrolytes that you have to distinguish from the weak electrolytes, that is the strong and the weak bases. And we talked about how to do that in 4.3 part 1. But in context here, you'll see there's a few things that can trip you up a little bit. It's a little on the technical side, but I think with practice you'll be pretty good at it. So what is exactly going to be the tripping up point? Strong acids and bases are written as ions, but the weak ones are not, and it's the weak ones that are going to cause trouble. So for example, if it's a strong acid like HCl aqueous, and if the molecular equation shows it this way, and I want to write it in the as a complete ionic or net ionic, I show the two ions the way they actually exist in solution, that is split apart. But if it's a weak acid like acetic acid, and this is what I generate from the molecular equation, I don't split that thing up as a hydrogen ion and an acetate ion. And the same would hold for weak bases, but we're not going to emphasize those. So what we'll do, I think I have 6 or so examples we'll go through, and just go through one at a time and just see if we can understand the logic of it as we do it. So first of all, someone asks you, what is going to happen when nitric acid and sodium hydroxide react? The first thing you should do is at least highlight in your mind which are the positive and the negative ions involved here that might join up to form some kind of new product. And I just highlighted them in red here. There's the hydrogen and the hydroxide ion that may join up to make some new substance, or the sodium and the nitrate, and I think you know which it is. It's not the sodium and the nitrate; those are aqueous solutions. That's going to be those are ions that stayed in the aqueous state, stay dissolved. But the other ones, the hydrogen and the hydroxide, that's what forms the water molecule. So here's the molecular equation that we learned how to write in 4.3 part 2. It's all balanced already. There's nothing new here. The new part is now, how do I write the ionic equation? So first of all, do I show this thing intact, or should I show it split apart? It really is the question, is this a strong electrolyte or not? It is, so we're going to split it up. Is this a strong electrolyte? Yeah, it's ionic. That's a strong electrolyte. We split it up. Water, that's just water molecules, covalent. You don't do anything with that, just like with the precipitates before. But this, again, is a strong electrolyte, NaNO3. So the 3 substances are going to get split apart. That is the nitric acid, the sodium hydroxide, and the sodium nitrate when you write the ionic equation. The balancing hasn't changed, it's all the same. How do I now show the net ionic equation? That is, once I cancel the spectator ions, that is the sodium and the nitrates, what's left? Well, it's just hydrogen ions meeting up with hydroxide ions to form water. So the net ionic equation shows that. Cancel what's on both sides, redundant, that is the sodium and the nitrate ions are on both sides. Once they're canceled, what's left is the net ionic equation. Hydrogen ions meet hydroxide ions to form a new water molecule. What would you see, by the way, in the lab? You wouldn't see anything because you could neither see the dissolved ions nor the increase of water molecules, but you would be able to measure that something has happened. All right, let's look at another one. So here's what's different here is that this is a substance that's a solid, and that would change a little bit in terms of how we write the equation. First of all, the same logic. Find what the positive and the negative ions are. Oh, there they are. It looks like we're going to have an acid-base reaction. The other two, the magnesium and the chloride, they're not going to do anything. They'll just be in a dissolved state as before. All right, let's write the balanced molecular equation. We know how to do that, and this is what the equation is. And now comes the new part. How and what do I split up when showing the ionic equation? First, hydrochloric acid. Is it on our list of 7 strong acids? Yes, it is. It gets split up. Magnesium hydroxide is a solid, It's a solid. We don't split up anything. It exists exactly as shown here. Same with the liquid water. But this magnesium chloride, again, is a strong electrolyte, so it gets split up. So let's make sure we get the splitting right. 2 molecules of hydrochloric acid will give us 2 hydrogen ions and 2 chlorides. We don't split the magnesium hydroxide. We don't split the water. And here a single unit of magnesium chloride gives us a magnesium ion with a +2 charge and 2 chlorides. All right, what's left to cancel now to show us how do we get to the net ionic equation? I notice I have 2 chlorides on both sides I can cancel, and I think that's it. So there's nothing else to cancel. And this is a nice kind of representation of what happens. For every 2 units of hydrogen ions that attack this magnesium hydroxide crystal, which is a solid, this thing will end up in a dissolved state. The magnesium ions go into the solution as a +2 ion, and 2 water molecules are formed. And notice the chloride ions are just spectator ions, so they're not shown. They didn't do anything. The 2 chlorides were in the solution as part of the hydrochloric acid, and they're still in the solution afterwards. So yes, the molecular equation here shows MgCl2 aqueous, but it's, like I said, somewhat misleading. This net ionic equation is a much better representation of what's actually happening. Good. Let's try a couple more. Let's see how we do. This one is calcium hydroxide and acetic acid. So what's new here is I've introduced a weak acid, the acetic acid, to see how we'd write that. Do the same thing. Highlight the positive and the negative ions from the 2 compounds that might join. There it is, hydrogen hydroxide. Looks like an acid-base reaction. And later on in the course, when we have, I'm going to give you different reactions, and I won't necessarily tell you it's acid-base. That's why this part is also helpful to keep track of what kind of reaction it is. The other 2, the calcium and the acetate ion, they won't do anything. Those are soluble, so they will just be floating around in the solution when we're all done. The molecular equation, we know how to do that. Here it is. It's all balanced. And now comes the new stuff, the ionic and the net ionic. First, do we split up the acetic acid? No, it's a weak acid. Unlike hydrochloric acid in the last example, this is not a strong acid, so it exists predominantly is an intact set of molecules. So you just rewrite it as written, as if it were a solid or a liquid. This is an ionic compound, strong electrolyte. It does get split up. The liquids, of course, we don't. And here we do split this one up as well. So what are we going to split up? The calcium hydroxide and the calcium acetate. Here they are. The calcium hydroxide are split, calcium acetate, not the acetic acid. That's the part that's different. All right, now let's have a look to see what gets canceled in this reaction. The only 2 ions, the spectator ions, are these calcium ions. They're the only ones that actually didn't do anything. So when we're left over, we have this reaction that says, start off with mostly intact molecules of acetic acid, put them in this environment that has these hydroxides, you'll end up with nothing but acetate ions and water molecules on the assumption that you've added enough relative to the amount of acetic acid you have there. So that's a nice representation of what's happening in the reaction. The molecule is intact to begin with, and it goes into the dissolved state completely if you are in the presence of these hydroxide ions. All right, pretty good. Let's do another one. So what's new here? This one is the trickiest one because it involves sulfuric acid. And it's slightly controversial how you're going to write the ionic equations, the complete and net for reactions involving sulfuric acid. And you'll see my way of writing it is, well, I'll show you in a second. So first of all, like we did before, highlight the hydrogen and the hydroxide. Say, yes, I could tell this is an acid-base reaction. The potassium and the sulfate are going to just be soluble at the end. Write the molecular equation, nothing new here. And now comes the tricky part, writing the ionic equation. Now, if you follow the logic of what we said before, we should say, well, is this a strong acid? Yes, it is. If so, show it independent. Show the ions the way they actually exist in a solution. But the problem is that this thing is a strong acid with respect only to the first hydrogen, not the second. So I should split this up to do this properly and only show the first hydrogen separate from the hydrogen sulfate. If you look around on the internet, at different textbooks, now and then you'll see it written that way, but for the most part, people just go ahead and write it as if both hydrogens were in the solution with the sulfate. It's not technically true, but this seems to be the kind of predominant way that people are writing it. And since I didn't want you to get confused, I went ahead and wrote it that way as well. And on the exercises, it works that way as well on the website. However, technically, the more correct way I'll show you right now. How about this here? Potassium hydroxide, strong electrolyte, yeah, it gets split up. Another strong electrolyte, split it up. So this is the correct way to write it, but you will not see this on the web written like this. That is, the sulfuric acid usually is not written like this. Instead, this more questionable way, and that's why I put a question mark here, is the predominant way that you'll see it. And unfortunately, like the textbooks that I've consulted, they sometimes will do it what I think is the more correct way, this top way, and sometimes the second way. So for the poor student, that's just confusing. So I'm putting it here, and my bottom line is we're going to ignore this more, what I think is the more correct way, and go with the questionable way, just because that's what's kind of dominant. And this only comes up with sulfuric acid, so we don't need to make too big a deal out of it. Let's move on to the net ionic equation now. You'll see they're actually quite different depending on which that you start with. If you do this more correct way, it's only the potassium ions that are able to be canceled on both sides, because we went from having a hydrogen sulfate to a sulfate ion. This was one of the dominant parts of the solution before, but now it becomes just sulfate ions in the presence of hydroxide, just like the other weak acid example. However, this is how you'll see it written on the web everywhere, as if we had only hydrogen ions and hydroxide ions that were coming together to form water molecules. Notice also here I canceled the 2's. In the original equation we had 2 hydrogens with 2 hydroxides making 2 waters. If you can cancel out the common denominator, just go ahead and do it. So this question mark is here, but this is the way that we'll write these, and is the most dominant way you'll see around in the community. All right, enough of that kind of more complicated thing. Now let's look at this, I think, last one. Aluminum hydroxide, it's common in antacids with acetic acid. What are we doing here? It's a combination of a weak acid with a solid. So you're going to see there's not too much we're going to be able to cancel here. First of all, try to figure out that it's an acid-base reaction. Yeah, you see the hydrogen with the hydroxide. The aluminum and acetate will be in a dissolved state. Molecular equation, nothing new. We know how to do that. Now comes this part, the new stuff. Do we split up the acetic acid? No, it's a weak acid. Do we split up solids? No. Water? No. Only the aluminum acetate we would split apart. So you'll notice here, because there was nothing to split apart, well, there's nothing that I can cancel on both sides. So therefore, my net ionic equation and my complete ionic equation are going to be identical. So they kind of don't really give us new information. There's no new information to be had from the net. So if you're asked to write it, just kind of copy and paste down what you have in the ionic one. I think that's it. So what's confusing about this, I think, really is that sulfuric acid example, and I apologize if it seems like I was making too much of it. Write it the easy way. Just assume that both hydrogen ions are in solution with the sulfate. It's not consistent with what we're saying, but close enough. It'll keep you from getting frustrated. All right, good luck with these. Practice on the website, and again, we will practice together. See you in class. Bye.